I'm going to record this, not so much for the people who are slow in showing up today, but I had someone in my second period class who was having technical issues and asked for me to record this. So here we go. Let's kind of break the mold. I'm not going to give you a new formula today, so I'm not going to go over necessarily all of those old formulas either. In fact, today we have a couple of theorems, 3 of them. They are theorems which will help you to solve problems, so they're more of the formula variety. Then you're not going to really use them in a proof. So no more proofs, but here we go. Let's pick a nice, simple, easy shape to deal with, find its area and all that. What shape do you want to use?
Square.
A square sounds like a great idea. In fact, let's draw 2 of them. So that is a square. I'm telling you that it is a square. You don't have to prove it or anything like that. And here is another square. And without knowing anything about these 2 squares, I can say that they do have a relationship. In fact, they are
Similar.
They are similar. All squares are similar. Just to remind you, similar means that their sides are in a specific ratio. And whatever side I make this thing, how big is it? What should we make it?
2.
2 sounds good. Well, all of these sides are 2. How about this guy?
6.
7.
6, is that what I heard? So all of these guys are 6. And 2 to 6 is the same thing as 2 to 6 is the same thing as 2 to 6, and so on. The other aspect of similarity is that all corresponding angles are congruent. Well, we know it's a square, so we know that they're all right angles, and all right angles are congruent. After all, that was our first theorem of the entire year. Okay, what is the ratio of lengths from one square to the other square?
2 over, 2 is 6 is to 6, or 2 is to 6 is 2 is to 6?
Okay, the ratio I'm hearing is 2 to 6, which is not wrong, but also not full credit. Better than everyone else who has said absolutely nothing. If I said, what's the ratio, and you said 2 to 6, if I wrote down the ratio of lengths was equal to 2 to 6, what's wrong with that?
3?
1 to 3.
It's 1 to 3, yeah, equals 1 to 3. We always reduce. Hey, what lengths am I talking about here?
Side.
We're talking about the side lengths. Anything else? What's the perimeter of this square?
8.
8. What's the perimeter of this guy?
24.
24. What's the ratio of 8 to 24?
1 to 3.
1 to 3. What is the length of this diagonal?
2. Wait.
2 weight.
2 root 2.
2 root 2. It's a 45, 45, 90 triangle. 2 root 2. What's the length of this diagonal?
6 root 2.
6 root 2.
6 root 2. What's the ratio of their diagonals?
1 to 3.
1 to 3. A little bit more enthusiasm. Wake up, people. It's already like 10 o'clock. All right. What is the length of this apothem? And
1.
Stella's.
1.
Okay, 1. And what about this apothem?
3.
3. What's the ratio of their apothems?
1 to 3.
1 to 3. What is the radius of the square on the left?
1 as well.
1 root 2, as a matter of fact.
Oh.
The apothem of the radius goes like that.
Oh.
So it's half of the diagonal. 1 root 2 and 3 root 2. What's the ratio? 1 to 3. Let me ask you again. What things have a ratio of 1 to 3 here?
Squares.
What? Any of their
Everything.
corresponding lengths. Not just their sides, not just their apothems or their perimeters, any corresponding length. What is the ratio of their areas?
1 to 3.
It is not 1 to
No.
3. What
It's,
is the area of the square on the
4 and 36.
All right, area equals 4, area equals 36. Hopefully not a formula which I have to remind you of. So what is the ratio of their areas?
1 to 9.
1
to 9.
1 to 9. Okay. What is the relationship between 1 to 3 and 1 to 9? Kayla, you're muted and kind of glitchy.
1 to
What was your response there? What's the relationship between 1 to
like 1 to 3 squared?
1 to 3 squared. That's it. Here is our first theorem. If two figures are, what was the big deal here? Similar. Then the ratio of their lengths squared equals the ratio of their areas. You guys seem unconvinced, so let's pick another set of similar figures. This time let's use a
triangle.
A triangle. Great, let's do some similar triangles. Is there a specific triangle you have in mind? Do you want to do the equilateral triangle? Do you want to do
Right triangle.
a right triangle? Okay, is there a specific right triangle? They have to be similar. Do you want to do like the 3, 4, 5 or something?
Yeah.
Okay, great. The 3, 4, 5 triangle, and that would be similar to a
6, 8, 10.
6, 8, 10. Okay, sure, fair enough. 6, 8, 10. We agree that these guys are similar?
Yes.
SSS similarity, all that good stuff. What is the ratio of lengths?
1/2.
1/2, 1 to 2. I love it. What is the area of this smaller triangle?
6. Wait.
I like 6.
6.
Yeah,
And 24.
area equals 24. What is the ratio of their areas?
1 to 4.
1 to 4. Did it fit the bill? If two figures are similar, they are similar, then the ratio of their lengths squared is the ratio of their areas.
Yeah.
1/2 squared is 1/4. Should I do another one? Are we good on this? Should I do a nice generic one?
What do you mean?
4.
Like instead of putting real numbers, what if I said that these two circles are obviously similar? All circles are similar. And I'll make this have a radius of A and this one have a radius of B. What is the ratio of their lengths?
A over B.
A over B. A over B. What is the area of my small circle? Pi r squared, but r is A, so pi a squared. What is the area of my big circle?
Pi B squared.
Pi b
Pi
squared.
b squared. When I compare their areas, what cancels out?
Pi.
Pi. And I'm left with a squared over b squared. Did it work?
Yes.
Yeah.
Yes. A over b squared is a squared over b squared. All right. You guys seem incredibly low on energy. Can we stand up, shake it out a little bit?
I'm good.
You are the worst, Stella. You've been yawning up a storm. Oh, I'm good.
I'm answering all the questions.
You have, but with a yawn, with a sigh, with a. I'm gonna stand up and harass a cat. All right. Come on, people. Get up. Stretch it out. I've got one stretch from Michaela. Nothing else. A yawn. Campbell, this is what I'm talking about.
Little stretch.
Jack has fallen asleep on his own hand. Good stretch, good stretch. Ryan, you with us? Comatose over there? Okay. Is there a coffee shortage?
I don't
No.
drink coffee.
You don't drink coffee. Okay.
No.
Maybe this is part of the problem.
How do you not
Blueberry
drink
coffee? My new favorite
It
thing.
tastes so bad.
No,
I can only
it's
drink
so
it if it's like
Sugar-
in a frappuccino that has 1,000,000 grams of sugar or whatever. Otherwise, I can't drink it.
Okay. Tomorrow, grab yourself a 1,000,000 of sugar frappuccino. Let's do this thing right. At least you were excited about something. What's up, Kayla?
There's a Starbucks like drive-through that's kind of near my house, and I've been making my mom take me there to like refuel on coffee.
There you go. Something you guys are passionate about. It's not similar figures. Anyway, here it is. One of my favorite theorems of chapter 11, definitely. We have 2 more theorems to go. I don't think any of them are hard. I think what people have a hard time with is they mix up the theorems. Okay, so they take that one and they're like, oh yeah, ratio of lengths squared equals ratio of areas. I'm going to apply that to everything. Where, just to remind you, it only works if the 2 figures are similar. There we go. Campbell's like wiping the crunchy eye boogers out of his eye, shaking it up. Now Andre's like yawning so large that I could have taken that hat and stuffed it in there. Like, oh. All right. My next 2 theorems specifically involve triangles. And I'm going to draw some triangles over here. In fact, how many triangles have I drawn?
3.
3. Yes, I'm only interested in the 2 non-overlapping triangles. And specifically, I'm only interested in that length and this length. So that first length, how big is it?
10.
10. Great number. I like 10. What about this one? How big is that?
5.
5. Okay. What is the ratio of their areas of this triangle to that triangle? Triangle 1 to triangle 2. What is the ratio of their areas?
1/2.
It is 1/2, although if we go that way, you should probably say 2 to 1 instead of, yeah. So here's the magic thing. These 2 triangles are not similar. Agreed?
Agreed.
Agreed. I got some nodding. All right. This one is an obtuse triangle. That one is an acute triangle. Not that we can really technically tell, but we have no reason to believe that these 2 triangles are similar. So I'm not just going to square their areas. On the test, about half the people square the ratio of lengths. I get the answer of 100 to 25 as often as the correct answer. Of course, I don't have exactly this problem, but that's what people do. So what I'm going to do is I'm going to do my best to figure out what that ratio of areas is in kind of a traditional way. I don't know if you can tell, but that line I just drew in is green. I made it a right angle. What is that green line?
Oh, the
The
altitude
height?
or the whatever.
I heard the altitude, the height, and a extra whatever in there. Thank you for the correct answer, and a whatever. I'll take it. I'll take it. Sure, it is an altitude or a height, not a whatever. All right. Sorry, it's the altitude or the height of which triangle?
The big one. Both. Wait, no. The one on the left and the big one.
And the one on the right as well. All 3. If none of you have energy, then I'm just going to have to like up my energy level. All 3. It is the height of all 3. It is perpendicular to all 3. Starts at the vertex of all 3 and is perpendicular to the opposite side. So the area of the triangle on the right would be 1/2 its base, which is 10, times its height, which I don't know. I will label it h. And I'm comparing that to 1/2 its base times its height. Oh, it has the same height. Ooh, what cancels out on this ratio?
Height.
The height most certainly does, and that's the important bit. What else cancels out, though? The halves do every single time. And in this particular case, because you chose, past tense, you chose 10 and 5, I can reduce, and the ratio of areas is 2 to 1. which was the same as the ratio of the
Nice.
bases. So these two triangles had the same height, and the ratio of areas was the ratio of bases. Here comes my second theorem. If two triangles have the same height, then the ratio of their areas equals the ratio of their bases. No squaring involved. We've got one more theorem to go. Woo! One more theorem. I apologize to poor Baxter, who's going to have to watch this as a video and see your deplorable amount of. Look at Stella yawning there. Jeez. What is wrong with you people? Then there goes Terrence. Look at that. Look at that. Jeez.
As you said,
Stella's yawning. Stella's yawning. Stella's
Stella makes me yawn. Even
Yeah.
when we're on FaceTime and she yawns and I yawn.
You guys are the worst. The worst. We've got one more theorem to go. Can someone please quit yawning and maybe guess what this last theorem is?
about the angles.
It has nothing to do with angles, but you're playing and I like it. Who now I know? What did you say? Steph? What's the last theorem? Someone guessing last theorem.
If
Good start.
two,
Yeah. Still trying.
I don't know. Have the same base, then RA equals RH. Did I get it?
Bam! Stella G. Yay! And finally someone has a mouth open, not to yawn, but to like say something smart and then to celebrate. Yay! Yeah! There has been a lot of good smart things, but a lot of yawning too. All right, let's see if we can draw that in, see if it makes some sense. I'm going to draw in two triangles here, which have the same base. Okay. That is the height of the smaller one. How big do you want to make that?
6.
6. This is the
4.
height of the larger one. How big do you want to make that?
12.
I didn't quite catch that.
12.
Let's go with 11 so I don't have to do this reducing bit, okay? Like that 12, 6 and 12, you know, they reduce. I'm just going to go with 11. Sound okay? So this is the base. I don't know how big it is. I don't care how big it is. I can't find out how big it is. I can't find out what the area of either of these triangles are, but I can figure out their ratio. So here we go. The ratio of areas is 1/2 base, whatever the heck it is, times height, 6, compared to 1/2 of base, whatever the heck it is, times 11. I'll put these in parentheses just to make it a little clearer. What cancels out of this ratio?
Half and base.
Half and base. Half and base. The ratio of their areas is merely
6 to 11.
6 to 11, which happened to be the ratio of their
Heights.
heights. I wish I could see Terrence's screen right now because he's getting something out of this that the rest of us aren't. All right, and there it is. These 3 theorems. I will tell you, when I put problems like this on the test, I get about half of my student body who uses these 2 theorems for everything. And about half of the student body who uses this theorem for everything. No, you use this one when the figures are similar, and you use these ones when 2 triangles either have the same base or the same height. Making the sense?
Yes.
Okay, I'm gonna stop the recording.